we have that opportunity, then we shall demonstrate on hardware. Okay. So in VLSI Design Lab, that basically we have two different types of job here we have to do. Okay. So one is that logic design using hardware description language, that is HDL, and here we are using the Verilog HDL. That is the first part. And out of 10 experiment, 6 to 7 experiment will be covered using this Verilog HDL. Okay, so it is one type of programming language, and you have to learn that. And last 2-3 experiment is based upon the circuit simulation, that is using SPICE, something like PSPICE, and you are already familiar with the SPICE environment. Okay, in your ECN lab or maybe in some other laboratory, you have used that SPICE simulator, and here also last 2-3 experiment, we are going to simulate different MOS circuits by using SPICE simulator. Okay. So coming to the first part, that is Verilog HDL. Okay. And so before going to that topic, so let us explore what is our objective actually. So if you take a look, that VLSI industry is one of the fastest growing industry. Okay, so and just refer to this table. Okay, so how that complexity, okay, how that number of logic components inside the integrated circuit drastically increases with respect to years. Okay, so if you look at okay, just see that table. Okay, around year 1958, okay, that transistor was invented. Okay, and the MOS transistor. Okay. And another one thing that is when we are talking about VLSI, so you can say that the VLSI here we can use the BJT as well as we can use the MOSFET. Okay, but in 95% cases, okay, we use the MOS transistors, because there are some advantages by using MOSFET compared to BJT. Okay, that you know that MOSFET it is much more easier to fabricate compared to BJT. Okay, it's much more easier to fabricate compared to BJT, while BJT requires some extra steps. Okay, BJT requires some extra fabrication steps, which makes costly. And apart from that, you know, BJT is not thermally stable. There are lots of leakage currents, which will create a big problem if you go for integrated circuit design. So that's why for all those limitations, we are not going for that BJT. Okay, to design integrated circuits, we are going for the FET, MOSFET. Okay, the MOS transistors. So today's VLSI, you can say that is all about the MOS VLSI, not BJT VLSI. So we are using the MOSFET to design it. Okay. So just see the table. So that single transistor was invented in the year 1958. So we can say the complexity level is 1. Okay. After that, by combining a few transistors, let's 4 or 5 transistors, we can design different logic gates, NAND gate, NOR gate, etc., etc. And that is called the unit logic. Okay, unit logic means the number of logic gate is 1. Number of logic gate is 1. So then by combining different logic gate, okay, we can design different logic circuits, digital circuits, such as by combining logic gate we can go for flip-flop, by combining logic gate we can go for multiplexer, we can go for adder, etc. So that is called single function. So single functions means it will implement one particular function such as addition. Okay, so here that complexity level is 2 to 4. So 2 to 4 is actually the complexity level is measured in terms of the number of logic gate is involved. Okay, the number of logic gate, you know, that different types of logic gates are used. Okay, NAND gate, NOR gate, AND or NOT. All those types of logic gates are there. Okay. So generally, when we are talking about the complexity level, okay, we refer to the NAND gate. Okay, we refer to NAND. And by combining multiple logic gates, we can go for multiple complex functions. Okay, then followed by that, we have a medium scale integration MSI, where 20 to 200 number of logic gates are involved. then large-scale integration LSI, and then VLSI. And actually now we are in the VLSI age. Now we are not in the VLSI, but still we use the term the VLSI, very large-scale integration. Okay, so where millions of transistors are present inside a logic chip, inside integrated circuits. So you can imagine what will be the complexity level. It's very difficult to handle. Okay. Now, so this is the simplified VLSI design flow. Okay. So to design any VLSI circuits, so first you have to specify the system architecture. That means which type of system you are going to design. Suppose you are going to design a processor, or you are going to develop one arithmetic logic unit or multiplier or whatever. So that is your system specification. Okay. And at the same time, what will be the tentative power consumption, area requirement, all those things will come under system specification. That is basically summary of your work. System specification means the summary of your work. Okay. Then functional design and functional verification. The next stage is functional design and functional verification. Functional design and functional verification means what are the different blocks are required. Okay, what are the different blocks are required to design your circuit, means to design your system. For example, if you are going to design a dedicated processor using VLSI design technology, okay, so what are the different sub blocks of a processor? There may be arithmetic logic unit, there may be a bunch of registers, there may be a control unit. Part by part. Okay. So you have to make sure that after combining different blocks, okay, you will get your desired output. So that's why there will be some verification stages. So functional design means all the sub blocks are connected together, and you have to make sure that those, after connecting different sub blocks, you are getting expected output. So that is basically verification. Okay. And each functional block, so let's talking about arithmetical logic unit. Okay, so inside the ALU, there may be addition, there may be subtraction, multiplication, division, so different types of operations are performed. Because our main focus is on the HDL, hardware description language. So the hardware description language is used to design this logic. Okay, the different logics, suppose adder, subtractor, flip-flop, multiplexer, decoder, etc., etc. We can design different digital logic. Okay, and at the same time we can verify its output. And again, suppose you are talking about adder. So adder is a combination of logic gate, and logic gate is a combination of transistors. Suppose if you are talking about half adder, so half adder is a combination of one XOR gate, you know, sum is a XOR function of A and B, and your that carry is a product, this AND operation of A and B. Okay, so actually what is XOR gate, what is AND gate? So you know the symbol of those logic gates, but a symbol is just for a representation. So actually those gates are designed by using MOS transistors. Okay, so after logic design stage, you have to design each gates used in logic design by using its transistor level diagram. That means each gate will be converted to its transistor level schematic. So that part is called the circuit design. See, the logic design is at the top, then the next part is the circuit design. Okay, so that means all the logic gates will be expanded, okay, will be designed by using its transistor level diagram. Okay, and of course the complexity of your circuit, okay, will increase. Suppose one XOR gate require 12 number of MOS transistors. So when you are representing that XOR gate in a circuit, it's just you are using only one symbol. But when you are representing the same XOR gate, okay, in the next level, in circuit design, basically you are drawing 12 transistors, not a single XOR gate. Okay. So circuit design, again, you have to go for verification steps, etc. Okay. And finally, the layout and all those things, and those things will be covered in your theory. So our main focus is on HDL, how we can develop different logics, different digital logics by using hardware description language. And the next step will be SPICE. That means how we can represent, how we can convert the logic gates by using its transistor level diagram and how we can simulate it. Okay. So after simulation, of course, we want the same result. Okay. How we can simulate it. Okay. So our focus will be on hardware description language as well as in the SPICE. So there are two types of hardware description languages that are used in industry. One is Verilog, another one is VHDL. Okay. One is Verilog, another one is VHDL. So it is called hardware description language because by using this language, you can describe a hardware. Okay, by using this language, you can describe a digital system. Okay. So here you can also model that a delay of a system, because you know for every digital logics there will be some propagation delay after applying input, so the output will be generated after some time, so some delay will be there. Okay, so that is basically called propagation delay. Okay, so even you can include the propagation delay, okay, inside your program, inside your code while designing those logic functions. Okay, so let us see how we can develop the digital system logics by using hardware description language. Okay. So if anyone having any queries, so please ask. So that after that, I shall go to the next stage. Now, for this logic design part, now since we are in the online platform right now, okay, so for offline platform, the different tools are used, okay, in our VLSI lab. But since we are in the online platform, so here we are using some tools. So that will run from browser directly. Okay, so no need to install any software for this lab. Okay, for the first stage, that means for that hardware description language, Verilog part. Okay, so no need to install any software. So it will directly run from the browser. But as you know, it is an online tool. Sometimes there may be some issues. Sometimes the server may be down. Okay, poor connection, etc. Those things will come, I'm telling. And then you have to just wait or you have to retry for that. Okay. So all of you open the browser. So if you are using mobile phone, it's difficult to do that. So my suggestion, you just open your laptop and just I'm typing one link in the chat box, cbaplayground.com. You open that. Okay, pdaplayground.com. Okay. You open that link. Is it opened? So if anyone having any queries, so please ask. Otherwise, later it's very difficult to tell this process repeatedly. Whether you got that site, is it opening?
Yes, sir.
Okay. Then see, there will be a lots of login options there. Okay, so at the top you will see, so there you can log in using your Google account, you can log in using Facebook account, or you can create a new account. After that you can log in. Okay, so simply you can go to that Google account option, log in using Google account. Okay, so you can log in using your kid account or your personal Google account, that's your choice. Okay, so you can log in that, but do not use Facebook, sometimes it creates a problem. So log in using your Google account. Okay. And after logging in, you should get this type of screen. You just check. You should get this type of screen, or blank screen will come like this. So just respond after getting this.
Yes.
So those who already here in this screen, just type yes in the chat box. Because I have to make sure that all of you correctly configured that simulation platform. Because for every lab, you have to use it. So if you got this screen, just type. Then, so anyone having any problem? So please respond. Okay, fine. So after getting this, so what to do? So see here, we have two different windows. Just check. So please note it. Here we have a design.sp. Here we have a textbench.sp. Okay. So in the right side, we have a design window called design.sp, this one. The left side, we have a testbench.sp. So actually, what is design and what is testbench? So when you are writing any hardware description language program, that is Verilog program, okay, in the design.sp, your main code will be there. That means the code required to develop. Yeah, roll number 50. What is your problem? No response. Okay. So in the design.sp, you have to write the code that will describe your system. Suppose you are going to design for half adder. So what will be the code for half adder? That thing you have to write in the design.sp window. Okay, here. And see, there is a plus button. That means you can create a new file. But my suggestion, do not create a new file. Do not create a new file. Whatever the default tab you will get after login or after opening this one. Okay. So here you have to type it. Do not create a new file here. Be careful. Okay. Second thing, after typing whatever the code you are going to explore, after typing here, okay, always take a backup of your code in a notepad. Sometimes due to poor connection, sometimes due to server error, okay, that window might be refreshed and you will lose your code. So always take a backup of your code, or you can type the code in Notepad or any other text software, but not in MS Word. Okay, if you type your code in MS Word, it will change the format of your code, and this program Verilog is case sensitive and you will get errors. So you can type the code in Notepad, and from Notepad you can paste here. Okay, no problem. And the left side, the testbench.sp, that is for testing your design. That means whether your design is correct or not, okay, whether you are getting expected output or not. For that, we have to write a couple of codes. Okay, few lines we have to write. That is basically testbench.sp. So design part, you will okay, here you will design the main hardware. Okay, the model, you will model the main system. And in the testbench.sp, here you have to write few codes to test your design. And how we test one digital system. Suppose you are going to perform an experiment of adder, a full adder. How to test it? Can you tell? Suppose I am designing a full adder. So how to test the full adder? Whether it is working or not. What is the process? Anyone? Can you tell? So in your digital electronics lab, how you verify your design? Suppose you have designed one multiplexer and gate or whatever, anything. So how you design? How you verify whether your design is correct or not? Anyone?
Run the code and see the signal.
No, see the signal means suppose you are going to design one JOR gate. So you have two input A and B and output is Y. So how you will verify it? What is the input-output relation of any digital system? How generally we represent the input-output relation of any digital system? Using a table that is called, what is the name of that table?
Truth table.
Truth table. Here also, in the test bench, we have to write a couple of code so that we can verify the truth table. Suppose I'm going to design one, let's half adder. We have two input A and B, output will be sum and carry. So two input means total 4 combination will be there. So we shall apply A0, B0, A0, B1, 10 and 11, and we shall check whether we are getting expected output or not. Okay, so that is basically the test bench. So test bench is used to test. Here we shall apply few input and we shall check whether we are getting expected output or not in form of wave. Okay, 0 means low, 1 means high, like that. So this is the next thing. Okay, so let's start writing code. Then I shall tell the rest of the parts. Okay. So for any Verilog code, okay, I'll zoom that. Yeah. So I'm going to type hardware, this program for hardware, half adder. Okay, so Verilog program for half adder. So those double slash indicates it's a comment line. Okay. And each Verilog program starts with a module. Okay. So you have to type module. Okay. So do it module space followed by module name. Module name means basically here in the library, this Verilog code will be saved as a module. That means later you can reuse this module. Okay. So let module half adder. You can give any name. Okay. Module half adder followed by bracket open close. Okay. Module half adder. Okay. Then, yeah, few things you have to remember that this module name should not start with a number. Okay, it should not start with a number. It should not start with a special character. And there will be no space between this. Okay, so if you want to write in a different way, you can give underscore like that. There should not be any space. Okay. So for any Verilog program, it will be like this. Just a minute. The next step, inside this module half adder, here you have to write inside this first bracket, here you have to write what are the different pins, means input, output are there. You have to specify the input and output ports. Okay, in Verilog we use the term port. Okay, which one is the input, which one is the output. So now there are different techniques to write that. We shall follow the simpler one, the first very basic one. Okay, so what are the different input output pins are there? So can you tell me what are the input and output of a half adder? Anyone? We are going to implement half adder. What are the input and output of a half adder circuit? Can you tell? Anyone?
Sir, two input will be there, and sir, we will get sir two outputs. Sir, one is output sum and carry outs.
Yes. So we have two input. One, let the input is A and B. Okay, and the output will be sum and carry. Okay, the output will be sum and carry. And here you can write it in a different order, but my suggestion, always write output first. Let I am taking S as a output, CO as a carry out, A as a input, B as a input. S, CO, A, B. Okay, S stands for sum. You can give different name, but here I am giving S, CO so that later I can identify. Okay, S, CO, A, B. First output followed by input. Okay, you can write input followed by output, that's okay. But just make one practice. It will help you to identify errors later. Okay, and follow this steps for all Verilog programs. Okay, this one. The next line will be which one is input and which one is output specified. Okay, so output S, CO. Okay, also you can write in a different line output S semicolon, next line output CO you can write. Okay, similar to variable declaration in any programming language. Okay, and input A, B. This one. Output S, CO, input A, B. Also you can write input first, later output. Here, no need to maintain any order. Okay. So we have total 4 pin, sum and carry out. This is the output. A and B, those are the input. Okay. So this is the module description actually. Till now we have completed. We are going to design one half adder. We have 2 input A and B. The output will be sum and carry out. Okay. Now we are going to model the system. Now there are different types of modeling. Okay. Now in Verilog, generally 3 types of modelings are used. Okay. First one is the gate level modeling. The basic one is the gate level modeling. So what is gate level modeling? There are already some logic gates are stored inside the library. Already there are some logic gates are stored. That means the basic logic gate, AND gate, OR gate, XOR gate, etc., etc. Those gates are already pre-designed and they are present inside the Verilog library. So we can call them. Okay, we can specify the input and output. Okay, like that. So here in the first program, we are going to use the gate level modeling. Okay, gate level modeling. The gate level modeling, so you can call any gate by using its name. And you know that. So what is the relation between how we can compute S for half adder? If you forgot, just take a look here in this diagram. So sum is basically what? XOR operation of A and B. The input is A and B, so sum is basically XOR operation of A and B. And what about carry? So carry is basically AND operation of A and B. Okay, so this is the diagram. Okay, this is the diagram by using the logic gate. So we can model by using, that logic gate. Okay, so here, the first we are calling the XOR gate, XOR. Okay. Then you have to give some label name. Label means there may be multiple XOR gate, there may be multiple gates you are using. So give any label name, let A1. A1 is just a user-defined name. Okay, it's a label name. Followed by here for XOR gate. Now see that by using this keyword XOR, the XOR gate may be a 2-input XOR gate, the XOR gate may be a 3-input XOR gate. So in Verilog, the first parameter which will be passed inside the bracket, that should be the output. And all other parameters will be the input. The first parameter after this bracket, suppose XOR A1 within the first bracket, the first parameter we are going to pass. So that is basically the output of the logic gate. Suppose here in this case it is XOR gate. It will be the output parameter. All other parameter will be the input parameter and it will be followed by comma. That means in our case, which one is the output? Which one is the output of XOR gate? In this program? S. S. So first we have to write S here. Then comma. Then we have to pass the input parameters. The input parameter means it's just A and B. So S, comma, A, comma, B. That's all. So we are calling one XOR gate to compute sum. Okay. So XOR, give some label name, let A1. Okay. Then first one is the output. Second one is the second and third is the input. If it is a 3-input XOR gate, suppose to design full adder, sum will be A XOR B XOR C in. Then you have to use 3 inputs. So first one will be the output followed by all the inputs. In the same way, I'm calling the AND gate because the carry you will get from AND gate. So AND give some label, let A2. Okay. Here the output of AND gate will be what? Carry out CO, comma, input will be A, comma, B. So that's all. This is our program. Okay, using gate level modeling. And finally, you have to close this program by typing end module. There should not be any semicolon after that. So the Verilog program will start with a module, and end module means this program is just finished. Okay, the module followed by module name. Then you specify what are the input output. My suggestion, you write output first followed by input. Then you specify here which one is the input, which one is the output. Then you use different modeling technique. Here we are calling the inbuilt logic gates to implement our logic, the XOR gate and AND gate. So that's a half-adder circuit. Okay. Now here we have to develop the test bench code for this. Okay. So how to write the test bench? So this is a little bit different. Okay. So it will be better if you just write it in your copy. Okay. So for test bench, you also type the same module followed by one module name. Suppose our module name is this one. Okay. So here half-adder underscore test. I'm writing in this format. You can give any name, but my suggestion, you just put any name underscore test so that we can identify. So this program is called your test bench. Okay. Now, interesting thing here, no need to give any parameter after this because this is for just testing. This is not an individual module. This module will test this one, this design. Okay, so this half-adder underscore test module will test this module half-adder. Okay, this one. Then whatever the input parameters and output parameters, see how I am declaring this. The input parameters here we have A, comma B, but in the test bench, that means we are applying some test vectors. Sometimes A will be 0, sometimes A will be 1, like that. So in the test bench, while assigning the input, it will be declared as register type. So REG A, comma B. See the change. Here we define it as an input. So here it will be REG A, comma B. Okay. And the output S, comma C0. So those are the driver, means the output side port. Okay. They are called OIR. S, comma CO. See the change. The input in the test bench, they are declared as REG register type, and the output are declared as OIR type, S, C0. Okay, this one. Then we are going to test this module. That means we have to call this module. Just copy this module, whole, paste here, and give some label name. Suppose L1. Half-adder, L1, then you copy, means whatever the parameters are there. This. If you are typing manually, make sure that it is in the same order. It is something like function calling. In a function, when you are passing the parameter, you have to maintain. You know there are two types of things, two types of calling, call by reference and call by values. Here also we can do that. Okay, so but here suppose the first one is S, so make sure that here S is present. C0, A, comma B. Also, you can take different values. Suppose instead of taking A and B, we can take XY. Instead of taking S and C0, we can take different value, PQ. But make sure that when you are passing those values, it will be in the same order. Those who are familiar with the programming, okay, so they can correlate this matter. Here, you can take any different name. Instead of taking AB, you can take XY. Instead of taking SC0, you can take whatever, anything. But when you are calling this, okay, the first one will be sum, then carry out, then A, comma B. Okay, those values will be there. Suppose instead of AB, you can take P and Q. No problem. So this will be mapped with this one here. And this value will be passed to this one. Okay, like that. So half-adder L1 is comma C0, comma A, comma B. I think all of you have completed up to this part. Anyone having any query up to this? And always take a backup of your code in a notepad. Now we are going to apply the test vectors. That means different input. A will 0, B 0, etc., etc. For that, this loop will start with the initial followed by begin. Okay, so those are the common syntax for writing any test bench: initial, begin. And finally, there will be one end statement, and you know all module is finished by using this end module statement. Okay, end module will be there, initial, begin, followed by end. Whenever there is a begin means the starting of the bracket, and end means the end portion of the bracket. So we have to place our code here. Now we are going to write 2 lines of code. So that is basically simulator specific. For different simulator, the things will be different. Okay, if you use a different software, then those lines might not be required. But here in this platform, we need that. Okay, so dollar. So make sure that those codes are present in your test bench. Otherwise, you will not get output. It will be compiled. Your code will be compiled, but you will not get any output. Okay. $dump file. Okay. Within this, you have to type this $dump file. Within this, dump.vcd. Then $dump pads. Actually, so this dump.vcd file will contain all the simulation data. When you are applying the different input of A and B, the dump.vcd file will contain those simulation data, and finally it will plot the graph. Okay, $dump file, $dump pads. Okay. Then in the next stage, now we are applying the values. Okay, so we have A and B, so we can write A equal to 0, semicolon, B equal to 0, semicolon. Okay, so first step we are applying the test input A0, B0, and before applying the next input, that means 0 and 1, we have to give some delay. So #20. #20 indicates a delay of 20 nanoseconds. In Verilog, #20 means it's a delay of 20 nanoseconds. Okay, so A0, B0, #20. And there are some other technique to write, to apply this input. So later, the next class, we shall discuss it one by one. Till now, just here. Today, you just follow this syntax. Okay. So then you can just copy paste the same line. Then we can write A0, B1. Again, give some delay, #20. Then we can write A1, B0, #20. And then A1 and B1, #20. Now we have already applied all the input. Then we can terminate our program $finish by using this $finish. I mean, see, first we are applying 0, 0, and we are giving some delay. So without delay, if you apply the next input, it will not be reflected, Then 0, 1, then some delay. Then 1, 0, then some delay, and 1, 1, then some delay. Then you terminate the program $finish. If you do not write the $finish, then what will happen? It will run for a specific time, then it will be automatically terminated. Okay, that depends upon the simulator configuration. So be careful about syntax. There should be a semicolon at the end of each line. So just check here, okay, and complete your code. Just tell me when you are done from your side. Is it okay done?
Yes, sir. Up to is done.
Yeah.
Yes, sir.
So then we are going for the simulation. Take a backup of this design code and test bench code before running the simulation. Because the online simulator, sometimes due to poor connectivity, server problem, okay, that page might be refreshed and you will lose all the code. So take a backup of all the code in a notepad. Okay. Now follow the steps. You go for this one, language and libraries, this tab. Okay, language and library. So here by default those things are selected because we are using the Verilog language. So by default it is as Verilog, system Verilog or Verilog. No need to change it. No need to change anything here. Okay. The next tab, tool and simulators. See, there are some commercial simulators are available. There are some free simulators are available. So you can select this one. Just write the name Aldec Rivera Pro 2020.04. You can select this one, or you can select under free simulator. You can select this one. Okay, Icarus Verilog 0.9.7. This one. Okay. So you can go for this or you can go for this. Both will produce the same result. Sometimes this Aldec server, okay, might not might be down. So then you have to go for this Icarus Verilog 0.9.7. Now I'm using this one. No need to change anything here under compile option. The default option is just okay. Okay. And see here, there is one option, runtime. So runtime, as I told you, if you do not mention this $finish, that means here forcefully I am terminating the program. If you do not mention this, then your program will run for the 10 millisecond, then it will be stopped. But 10 millisecond is a long time. We do not want that actually. So that's why when your test bench is complete, then after that you just terminate your program by typing this $finish, because it is online platform, online simulator. Okay, so if you apply a long run time, sometimes you will not get the outputs. It's better to terminate your program when you have applied all the input. Okay. The most important thing is make sure that this one is ticked. Open EP wave after run. If it is not selected, you will not get the output actually. Means the graph will not be open. Okay. Open EP wave. So EP wave actually is the graphical window, the visualization window. So you will get that output in graph form. You have to select it. Open EP wave after run. Okay. And when first time you run this, if you are using Google Chrome, so there might be some, in the taskbars and pop-up blocked like this. Okay, some message will be there. You have to allow the pop-up. Okay, and again you have to rerun it. Okay, to get that. Okay, so now we are ready. We are going to run it, and click on run. See, I'm getting output, so you also check that. So those who are using Google Chrome, just see there will be some message pop-up blocked. You have to allow the pop-up and rerun. Those things are repeated 2 times, sometimes 3 times. Those things will come. So you can delete the repeated part. How you can delete it? You just select the signal. See here, you can select it. Suppose I selected S. Then you this one. Select C0, delete. Select A, delete. This. Okay. Now we have our input and output. Now, if you want to move the signal, suppose I want to display A, B, then sum will be there, because generally we are familiar with that pattern, A, B, sum and carry. So you can select and you can see, move up here. Okay. So you can select that signal and you can click up and down. If you are not getting this graph, in your simulation, there is no error, but you are not getting this graph, then what you can do, you can click here. Suppose this window is open, but there is no graph. Then you can click here, get signals. Okay, you will get one window. Then you click on your module name, half adder test. Okay, then click on append all. If you are not getting the graphs, this EP wave window is present but no graph is there, so then sometimes you will face this problem later. Okay, then you can click on get signals, click on the half-wire, this whatever your test bench name, half-adder underscore test. Okay, you will see all the signal will be present here. Then you can select individually or you can just click on append all. Okay, this one. So how to test it? You just click on any time scale here. Okay, see here the value A and B, the sum will be 0, carry will be 0. If you click here, check A0, B1, of course 0 and 1, sum will be 1, carry will be 0. If you click here, A1, B0, sum 1, carry 0. And if you click here, A1, B1, sum 0, because 1, 1, sum will be 0 and carry will be 1. Now see, this program, this will run up to how much? 80 nanosecond. Okay, because according to our program, okay, we gave the delay of 20, 20, 20, 20. So